The Q function is the tail probability of the standard normal distribution. Q of x equals 1 over root 2 pi times the integral from x to infinity of e to the minus t squared over 2 dt. It gives the probability that a standard Gaussian random variable exceeds the threshold x. Since this integral has no closed form, practical analysis demands tractable approximations. Two fundamentally different strategies exist for bounding Q of x. The Chernoff bound exploits a key insight. While the Gaussian tail integral has no closed form, its moment-generating function e of e to the sc equals e to the s squared over 2, computable in closed form. Minimizing the resulting exponential bound over the free parameter s yields a tight upper bound. Craig's formula takes a different route, rewriting Q of x as a finite integral over a bounded domain and approximating with two evaluation points. Both are exponential in x squared, but Craig's result matches the exact Q function almost perfectly. For the Chernoff bound, introduce a free parameter s greater than 0. For any z greater than x, the inequality e to the s times open paren z minus x close paren is at least 1. Multiplying both sides by the Gaussian density and integrating from x to infinity gives Q of x is at most e to the minus sx times the moment-generating function of z. For the standard normal, the MGF equals e to the s squared over 2. Substituting, Q of x is at most e to the exponent s squared over 2 minus sx for every positive s. This is the critical step and where the technique reveals its elegance. Differentiate the exponent s squared over 2 minus sx with respect to s. The derivative is s minus x. Setting this to 0 yields the optimal parameter. S star equals x. Substituting back, the exponent becomes x squared over 2 minus x squared, which is negative x squared over 2. The Chernoff bound is therefore, Q of x is at most e to the minus x squared over 2. Craig's formula begins from an exact alternative representation. Craig showed in 1991 that the Q function equals 1 over pi times the integral from 0 to pi over 2 of e to the minus x squared over 2 sin squared theta, d theta. To build a two-term approximation, we evaluate the integrand at two carefully chosen angles. At theta equals pi over 2, sine squared theta equals 1, giving e to the minus x squared over 2 with weight 1/12. At theta equals pi over 3, sine squared theta equals 3 over 4, giving e to the minus 2x squared over 3 with weight 1/4. Summing, Q of x is approximately 1/12 times e to the minus x squared over 2, plus 1/4 times e to the minus 2x squared over 3. Here are all three on a logarithmic scale from x equals 0 to 4. In purple, the exact Q function. In gold, the Chernoff bound, always above Q of x, tight for large x, overestimating by a factor of roughly 2 for moderate x. In teal, Craig's formula, visually indistinguishable from the exact curve. The log scale reveals the exponential tail structure and makes the relative error between approximations immediately visible. These approximations are the workhorses of modern wireless communication analysis. The bit error rate for BPSK modulation is Q of root 2 gamma, where gamma equals E sub b over n sub 0, the signal-to-noise ratio per bit. Over a Rayleigh fading channel, the average bit error rate requires integrating Q of root 2 gamma over the exponential fading distribution. Substituting Craig's two-term approximation converts this average into a simple closed-form expression involving the fading channel statistics. This technique generalizes to any fading model whose moment-generating function is known. What happens when the noise is not Gaussian? That boundary defines current research in robust and nonlinear detection.